Now we're continuing with section 4.6 and example 6, investigating a family of functions f of x equal to cx x to the power 4 minus 2x squared plus 1. If I'm trying to find how the shapes look like, and the first thing I want to do is to take the derivative of this because it's a polynomial. Derivative is going to be 4 cx to the third minus 4x, and I can factor x and 4, so 4x cx squared minus 1. And then f double prime of x, I'm going to take the derivative this way, and so it would be 12 cx squared minus 4, which is basically 3 cx squared minus 1, right? So here, the roots of both f prime and f double prime depends on this c. If c is a negative value, then neither of them have a root. If c is a positive value, then both of them, if the c is negative value, then the root of f prime is only 0. But if c is a positive value, the roots of f prime, there are 3 roots. And then for f double prime, if c is negative, there's no roots. If c is positive, there are 2 roots for f double prime. So solving the roots for f prime is going to give me negative 1 over square root of, if c is positive, it's solving for the roots, gives me negative 1 over square root of c and positive 1 over square root of c and 0. And then if you put those all in a number line, you get negative 1 over square root of 2, 0, 1 over square root of, c, and then you observe that from what we had before, it's going to be basically the signs are going to be negative, then it will be positive, then it will be negative and positive, and so you get increasing like that. And then the concavity, again, you will have 2 roots, and then using the concavity you will find the concave up, and then you find the local min and max over here, and then you graph it like that. So you get a shape like this. Now, what is going to happen when the c is negative? When c is negative, then you will only have, for f prime, you only have one root, that is 0. And then how it turns out, f prime is positive before 0, negative afterward. For f double prime, you will not have any zeros, so the sign doesn't change. It's going to be the same, and it's always going to be a negative value. And so in this way, you can, the graph will look like something like that, and there's no inflection point. Versus over there, you had inflection point because f double prime had roots, and the roots of odd order. So the 2 functions all depend on the positive or negative value for c, and it gives you 2 completely different shapes. And some of your WebAssembly questions ask similar type of parameterized curving, basically. Here's iCooker question 3 in section 4.6. It's asking, let f of x be this function, ax plus b over x, where a and b are both positive. What happens to f of x as a increases? Pause for a minute and then come back. Okay, so the answer to this is, let's take the derivative because we're discussing the critical numbers, and it's b times derivative of 1 over x, which is negative 1 over x squared, so negative b over x squared, a common denominator, and then find the roots, and x equal to 0 is not part of the domain, so don't worry about that. And so I get x equal to plus minus square root of b over a. As a increases, b over a decreases, and so both plus and minus b over a get closer and closer together. So the two critical numbers move closer and closer together. These are actually important parts when you're, let's say, in engineering. A lot of times you have to find parameterize functions derivative, and so like functions with parameters, to figure out how changing the variables. Let's say you're designing a circuit, you're designing a mechanical device, and so you want to figure out what values you have to put in, what strength you have to put in. So there are a lot of parameters like a and b in there, and then you want to calculate the derivative and so on and so forth, and figure out how your system is working better. And this is why you see a lot of parameters in the functions as well in here.